At the North Pole, temperatures can plummet to negative 45 degrees Celsius. On the dark side of the Moon, the temperature is minus 220 degrees. Out in the deepest reaches of space, the average temperature is 270 below, or 3 degrees Kelvin, just 3 degrees above absolute zero. But the coldest place in the universe isn't light years away. It's in Cambridge, Massachusetts, in a lab at MIT. Here, a team of scientists are building upon generations of research to study atoms at frigid nanokelvin temperatures, less than a billionth of a degree above absolute zero. That cold, these atoms enter a new state of matter called a Bose-Einstein condensate, or BEC, a discovery which delivered the 2001 Nobel Prize to MIT professor Wolfgang Ketterle.
When physicists try to understand matter, we usually make progress if we can prepare a system which still shows the phenomenon we are interested in, but it's the simplest possible system. And often one way to study new phenomena in nature is try to study them at very low temperature. When you cool down water, the water gets colder, everything slows down a little bit, but something special happens when you reach the freezing point. Then suddenly the liquid turns into a solid. We have now formed a phase of matter which has profoundly different properties. And you can experience them. I mean, you can experience the difference when you jump into a swimming pool and the water is frozen. So what we wanted to observe was a phase transition in a very cold gas. So you can see nothing happens, millikelvin, microkelvin, colder, 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 nothing happens. But then when we go from maybe a microkelvin to a few hundred nanokelvin, just a very small step, at that moment the phase transition to a new form of matter happens. And the new form of matter has been this long predicted phenomenon of Bose-Einstein condensation.
Ketterle's team first observed BEC in 1995. His lab notebook provides a glimpse of the eureka moment, the instant of discovery. But there's more to this story than just that single moment. This is a tale about how science advances through the combined efforts of uncounted collaborators and contributors. The study of BEC was a team effort from the beginning. In 1924, Indian physicist Satyendra Bose devised new statistics to analyze photons, particles of light. But no one would publish his radical ideas, so he wrote to the most famous physicist of his time, Albert Einstein. Einstein extended Bose's new mathematics from light to atoms, forming the basis for BEC theory. But it remained unclear if the equations were anything more than abstractions.
When Einstein derived the equation for Bose-Einstein condensation, he said almost verbally, "The equations are pretty, but is there any truth to it?"
Over the next decade, other researchers explored Bose and Einstein's math and predicted something surprising. If a gas could be kept from becoming liquid or solid, then at very low temperatures it would form a fundamentally new state of matter. But BEC would remain just a theory for decades, until the invention of a crucial technology, lasers. Like BEC, lasers emerged from decades of research collaboration. The theoretical framework behind lasers was proposed in the early years of the 20th century, but the first working laser wouldn't be built until 1960. Today, lasers are central to the work in Ketterle's lab.
All of the 10 plus beams of yellow laser light that travel through our experiment all come from this box right here. So when the light's coming out, it's about 1,000 times more powerful than your typical laser pointer, and it's squeezed down into a beam that's less than a millimeter in diameter. So it looks extremely bright if you actually see it hit any surface.
The beam travels through optical elements that reshape it before it reaches its final destination on the other side of the room.
If I walk through some of the labs and I see the laser beams bouncing back and forth between mirrors, I love it. It's elegant. It's laser light. It's cool.
It was only in the 80s that lasers became a tool for cold matter physicists, when teams of researchers developed laser cooling, a technique that cools atoms nearly enough to form BEC.
It's like trying to change the motion of a bowling ball by throwing ping pong balls at it. Right? Each ping pong ball is probably not going to change the bowling ball very much. But if you keep going, then you can begin to see significant effects.
When enough ping pong balls hit the bowling ball, it slows to a near standstill. In the lab, the ping pong balls are laser beam photons, and the bowling balls are the atoms of the gas. Laser cooling brings atoms down to microkelvin temperatures, millionths of a degree above absolute zero.
So if you ask me what is the difference between the air around us and the gas at microkelvin temperatures, I would say the atoms in a microkelvin gas move 10,000 times more slowly. This is very dramatic. In a normal gas, the molecules move at the speed of a jet airplane. In a cold microkelvin gas, the atoms just move at the speed of my hand. They really have come to a crawl.
But to form a BEC, the atoms need to be nearly standing still, about 1,000 times colder than laser cooling can achieve. To get that last critical fraction of a degree, Ketterle's group uses a second technique, developed by yet more teams of scientists in the 90s. It's called evaporative cooling, and it's based on a familiar phenomenon. The hottest atoms in a cup of coffee rise to the top and escape as steam. Blowing over the cup moves that steam away, and the drink cools. Ketterle students achieved the same effect by using radio waves to eject the hottest atoms.
By changing the frequency of those radio waves, we can blow away more and more atoms until we get to the critical temperature at which a Bose-Einstein condensate starts to form.
When the atoms transition from gas to BEC, something remarkable happens. Every atom in the cloud becomes indistinguishable from the others, forming a giant superatom. This allows scientists to study phenomena usually only measurable at quantum scales. In a normal gas, atoms move randomly, like the singers in an amateur choir, each a little off-key. But in a BEC, the atoms sing in perfect harmony. Ketterle's Nobel Prize was awarded for one moment of discovery, but as he points out, that discovery would have been impossible without decades of collaborations that produced the technologies his experiments require. 80 years in the making, BEC can now be created with the flip of a switch. It's become an important tool for a new generation of scientists studying extreme states of matter. This is how science gets done. Today's Nobel-caliber work becomes a stepping stone to whatever may be next.
It's actually a thrill to create situations where nature behaves in a way which nobody has seen until now. One can say, well, we have discovered all the continents, there is no island anymore to be discovered, it's harder and harder to discover new animals, but in science, that's still the place where discoveries take place. And that's a thrill.